Imagine a particle that doesn't just move fast. It moves faster than light. Not by a little, by a lot. It was never slow. It was never at rest. From the very instant it came into existence, it was already outrunning every photon in the universe. That's a tachyon, a particle that only exists beyond the speed of light. But here's where it gets strange. If you work through the mathematics, if you actually follow what Einstein's equations say about something moving that fast, you don't just get a fast particle. You get a particle that arrives before it leaves. You get effects that happen before their causes. You get a universe where the past is no longer safe. And that's exactly why this particle almost certainly cannot exist. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. There's a rule built into the fabric of reality, not a suggestion, not a guideline. A rule. Nothing that has mass can reach the speed of light. You've probably heard this before. It's one of the most famous results in all of physics. Einstein showed it in 1905 with his theory of special relativity, and over the past century, it's been confirmed by experiment after experiment after experiment. Every particle accelerator on Earth, every satellite in orbit, every GPS system guiding your car through traffic, all of them work because this rule is real. The speed of light isn't just fast. It's a boundary, a wall, a line drawn through the physics of the universe that says this far, no farther. At least, that's how most people think about it. And they're not entirely wrong. But the full picture is more subtle and more interesting than a simple speed limit. Because the speed of light doesn't just say you can't go faster. It divides the entire universe of possible particles into 3 separate categories. 3 fundamentally different ways of existing. And understanding those 3 categories is the key to understanding what a tachyon is supposed to be and why it creates problems so severe that most physicists believe it cannot be real. The first category is the one you're most familiar with. It includes every piece of matter you've ever touched, seen, or interacted with. Protons, neutrons, electrons, atoms, molecules, baseballs, planets, stars, you. Everything made of ordinary matter belongs to this category. These particles have mass, and they always move slower than the speed of light. Physicists call them tardions, from the Latin word for slow, though some prefer the Greek-derived term bradyons. These particles can be at rest. They can move slowly. They can move very fast. But no matter how much energy you pump into them, no matter how powerful the force pushing them forward, they can never quite reach the speed of light. They can get closer and closer, 90% of the speed, 99%, 99.999%. But they never actually get there. The speed of light is an asymptotic barrier for them. Something they approach but never touch, like a curve that gets closer and closer to a line without ever meeting it. The reason for this is deeply embedded in the mathematics of special relativity. As a massive particle accelerates, its energy increases. But the relationship between energy and speed isn't linear. It doesn't scale the way you might expect from everyday experience. At low speeds, adding more energy produces a proportional increase in speed in a way that feels intuitive. But as you approach the speed of light, the energy required to gain even a tiny additional increment of speed skyrockets. To go from 99% of light speed to 99.1% takes far more energy than going from 0 to 90%. And to go from 99.9% to 99.99% takes even more. The energy required to actually reach the speed of light is infinite. Not very large, not unimaginably large, infinite. The entirety of all energy in the observable universe, every joule contained in every star in every galaxy across 93 billion light years, would not be enough to push a single electron to the speed of light. This isn't a technological limitation. It isn't something we might overcome with better engines or more powerful accelerators. It's a mathematical consequence of how space, time, energy, and mass relate to each other. At the Large Hadron Collider at CERN, the most powerful particle accelerator ever built, protons are routinely accelerated to 99.999999% of the speed of light. These are the fastest massive objects humans have ever created. They carry enormous energies, each tiny proton packing the kinetic energy of a fast-moving mosquito into a package trillions of times smaller than a grain of sand. And yet they're still not at the speed of light. They're incredibly close, but the gap, however small, is real and unbridgeable. No amount of additional energy will ever close it. The second category contains particles with no mass at all. These are the luxons, from the Latin word for light. The most familiar luxon is the photon, the particle of light itself. Every photon that has ever reached your eye, every photon emitted by every star in the universe, every photon bouncing around inside a microwave oven or streaming through a fiber optic cable belongs to this category. Gluons, which carry the strong nuclear force inside atomic nuclei, are also massless. And if gravitons exist, the hypothetical particles that would carry the gravitational force, they would belong here too. These particles don't just travel at the speed of light. They must travel at the speed of light. They have no choice in the matter. A photon cannot slow down. It cannot speed up. It cannot stop. It cannot hesitate. From the instant it's created to the instant it's absorbed, it travels at exactly 299,792.458 kilometers per second. Not approximately. Exactly. This isn't a coincidence or a peculiarity of photons specifically. It's another consequence of special relativity. If you have no mass, you must move at exactly the speed of light. You can't go slower because a massless particle at rest would have no energy and no momentum, which means it effectively wouldn't exist. It would be nothing. The speed of light is the only speed available to massless particles. It's not a choice. It's their nature, their definition, their only possible state of being. So we have two categories: massive particles that always move slower than light, and massless particles that always move exactly at light speed. These two categories account for every particle ever observed in nature. Every single one without exception. Every particle detected in every experiment ever conducted. Every particle predicted by the standard model of particle physics and subsequently confirmed by observation falls into one of these two groups. But mathematically, the equations of special relativity allow for a third category, a category of particles that always move faster than light. These hypothetical particles are called tachyons, from the Greek word tachys, meaning swift, and they are perhaps the strangest things that physics has ever contemplated. The idea of tachyons didn't come from wild speculation or science fiction. It came from carefully reading the mathematics. In 1962, physicists Olexa Myron Bilaniuk, Vijay Deshpande, and E.C. George Sudarshan published a paper that took the equations of special relativity seriously in a way most people hadn't before. They looked at those equations and noticed something that others had seen but largely dismissed. Einstein's equations describe the relationship between energy, momentum, mass, and velocity. For ordinary particles, these equations work perfectly. They describe how energy increases as a particle accelerates, how mass and energy are related by E equals mc squared, and how velocity is always limited to less than light speed. But Belaniuk, Deshpande, and Sudarshan noticed that the equations didn't just describe particles moving slower than light. They also had valid mathematical solutions for particles moving faster than light. These solutions had been known for years, lurking in the mathematics like uninvited guests that nobody quite knew what to do with. Most physicists had dismissed them as mathematical artifacts, curiosities of the equations that didn't correspond to anything real. Just as the equation x squared equals 4 has two solutions, positive 2 and negative 2, even though negative numbers of apples don't exist on a table, the equations of relativity seem to have solutions that were mathematically valid, but physically meaningless. The three physicists asked a different question. What if these solutions weren't meaningless? What if the mathematics was trying to tell us something? What would a faster-than-light particle actually look like if it existed? Gerald Feinberg, a physicist at Columbia University, pursued this idea further and gave these hypothetical particles their name in 1967, building on the earlier work. He explored their properties in detail, working through the mathematics meticulously to see what such a particle would be like if it existed. And what he found was a particle unlike anything in ordinary experience. A particle whose properties seem to contradict everything we know about how objects behave. The first strange property is this. A tachyon would have what physicists call an imaginary rest mass. Now, I need to be careful here because the word imaginary has a specific mathematical meaning that's very different from its everyday meaning. In everyday language, imaginary means fake or made up, something that doesn't exist. In mathematics, an imaginary number is something much more precise. It's a number that, when multiplied by itself, gives a negative result. The imaginary unit, represented by the letter I, is defined as the square root of -1. When you square it, when you multiply I by I, you get -1. Imaginary numbers aren't fake or made up. They're essential mathematical tools used throughout physics and engineering. They appear in the mathematics of electrical circuits, quantum mechanics, signal processing, fluid dynamics, and countless other areas. Engineers designing bridges and electrical grids use imaginary numbers every single day. They're as real and as useful as any other mathematical concept. But here's where it matters for tachyons. In Einstein's equations, there's a famous relationship between energy, momentum, mass, and the speed of light. For an ordinary particle at rest, the equation simplifies to the iconic E equals mc squared. Energy equals mass times the speed of light squared. For a moving particle, the full equation is more complex. It involves the particle's momentum and its rest mass in a specific mathematical relationship. When you solve this equation for a tachyon, for a particle moving faster than light, the mathematics demands that the particle's rest mass squared must be negative. Not the rest mass itself, the rest mass squared. Now, when you square an ordinary positive number, you get a positive result. When you square a negative number, you also get a positive result. The only way to get a negative result from squaring something is if the thing you're squaring is an imaginary number. So a tachyon's rest mass would be an imaginary number. This doesn't mean the tachyon is fake or unreal in the everyday sense of imaginary. It means the tachyon doesn't have a rest mass in the traditional way, because a tachyon can never be at rest. Rest mass is the mass a particle has when it's standing still. But a tachyon can never stand still. It's always moving, always faster than light, and it cannot slow down to light speed or below. The concept of rest mass simply doesn't apply to it in the normal way. The imaginary mass is the mathematical signature of a particle that exists in a fundamentally different regime of physics from everything we've ever observed. The second strange property is even more counterintuitive. For ordinary particles, the relationship between energy and speed works the way you'd expect from daily life. The more energy a particle has, the faster it goes. If you kick a ball harder, it moves faster. If you put more fuel in a rocket, it accelerates to a higher speed. Energy and speed are positively correlated. More energy means more speed. Always. This is so deeply ingrained in our experience that it feels like it couldn't possibly be any other way. But for a tachyon, this relationship is inverted, completely flipped, turned entirely on its head. A tachyon with more energy moves more slowly. A tachyon with less energy moves faster. If you could somehow add energy to a tachyon, you would slow it down. Its speed would decrease, dropping closer and closer to the speed of light from above. The more energy you pumped into it, the closer it would get to the speed of light, but it would never reach it. It would approach the speed of light the same way an ordinary particle approaches it from below, getting ever closer but never arriving. The speed of light sits in the middle, untouchable from either direction, a barrier that separates two domains of existence. Ordinary particles approach it from below and never reach it. Tachyons would approach it from above and never reach it. Only massless particles like photons exist exactly at the speed of light. And here's the part that should make your head spin. If you removed energy from a tachyon, it would speed up. The less energy it has, the faster it goes. A tachyon with very little energy would be moving at many, many times the speed of light. Hundreds of times. Thousands of times. And a tachyon with zero energy would be moving at infinite speed. It would, in some theoretical sense, be everywhere at once. Everywhere simultaneously. This is the exact opposite of what happens with ordinary matter. An ordinary particle with zero kinetic energy is at rest, perfectly still, motionless. A tachyon with zero energy is moving infinitely fast. Everything about the relationship between energy and motion is backwards, mirrored, and inverted compared to the particles we know. Think about what that means for a moment. In our everyday world, you need energy to make things move. You need to burn fuel, exert a force, and provide a push. Motion requires energy. Rest is the natural state. But for a tachyon, it's the exact opposite. Motion is the default. Infinite speed is the ground state, the lowest energy configuration, the natural state of being. To make a tachyon slow down, to bring it closer to the speed of light, you would need to add energy to it. The tachyon resists slowing down the same way an ordinary particle resists speeding up. This isn't just unusual, it's a fundamentally alien way of existing. A tachyon doesn't inhabit the same physical reality that we do. It occupies the other side of the speed of light, a mirror domain of motion where all the familiar relationships between energy and speed are reversed. Now, I want to make something absolutely clear before we go any further. No tachyon has ever been observed. There is zero experimental evidence that tachyons exist, and we'll examine the full experimental record later. The concept comes entirely from mathematics. The equations of special relativity allow for solutions that describe faster-than-light particles, but allowing something mathematically is not the same as demonstrating it physically. Mathematics allows for all sorts of things that don't exist in reality. You can write perfectly valid equations for negative masses, for particles with fractional baryon number, for spaces with 4 or 5 or 26 spatial dimensions. These mathematical constructs can be useful for various reasons. They can help you solve problems, they can reveal hidden structure in equations and suggest new directions of investigation. But they don't necessarily correspond to real physical objects or particles. The tachyon is in this category. It's something the math permits, but nothing in the physical universe has ever confirmed. The reason this matters, the reason physicists care about tachyons even though they've never been found, is because of what their existence would imply. If tachyons were real, if faster-than-light particles actually existed and could interact with ordinary matter in any way, could exchange energy or momentum or information with the particles we know, the consequences would be catastrophic for our understanding of how the universe works. Not just surprising, not just challenging, catastrophic. The problems aren't technical or engineering problems that might be solved with cleverness or ingenuity. They're logical problems, contradictions, paradoxes so severe that they undermine the very concept of physical law. They strike at the most basic principle in all of science, the principle that causes come before their effects. But to understand why, to really see the problem clearly, we need to understand something fundamental about how special relativity treats the concept of time. And this is where things begin to get truly unsettling. In everyday life, we think of time as absolute. We think of it as something that flows uniformly, the same for everyone, everywhere, always. Right now is right now, everywhere in the universe at the same moment. If I snap my fingers at exactly noon, then it's noon everywhere in the universe at that same instant. The past is behind us, fixed, done, unchangeable. The future is ahead, open, undetermined, not yet, written. Events happen in a definite order, and everyone agrees on that order. I throw a ball, then the ball hits the wall. The throwing happens first. The hitting happens second. This ordering is absolute and universal. Nobody anywhere in the universe, no matter where they are or how they're moving, would see the wall break before I threw the ball. This intuition is deeply rooted in human experience, and for good reason. At the speeds we encounter in daily life, walking, driving, even flying in airplanes or orbiting in spacecraft, it's essentially correct. Time is effectively absolute at these speeds. The differences are so tiny as to be undetectable without atomic clocks. The order of events is fixed and agreed upon by all observers. But Einstein showed that this intuition is wrong. Not slightly wrong. Not wrong at the margins. Fundamentally, deeply, thoroughly wrong. At speeds approaching the speed of light, time behaves in ways that completely contradict everyday experience. Time is not the same for everyone. It does not flow uniformly. It depends on how you're moving. The most famous consequence is time dilation. A moving clock runs slower than a stationary clock. This isn't because the clock is broken. It isn't a mechanical effect of vibration or air resistance. It's because time itself passes more slowly for the moving object. This has been measured directly, repeatedly, with extraordinary precision. Atomic clocks flown on airplanes run slightly slower than identical clocks left on the ground. Moons created in the upper atmosphere by cosmic rays live much longer than their rest frame lifetime would predict. Because time dilation stretches their brief existence as seen from our perspective on the ground. Particles in the Large Hadron Collider experience time dilation so extreme that their internal clocks run at a tiny fraction of the rate of clocks in the laboratory. This is not theoretical speculation. It is a measured fact. But time dilation isn't the relevant effect for understanding why tachyons break causality. The relevant effect is something called the relativity of simultaneity. And this is a concept that most people have never encountered, even people who know about time dilation and length contraction. But it's absolutely critical for understanding the tachyon problem. Here's what it means. Two events that happen at the same time according to one observer do not necessarily happen at the same time according to a different observer who is moving relative to the first. Simultaneity, the idea that two things happen at the same moment, is not absolute. It's relative. It depends on your frame of reference, on how you're moving through space. Imagine you're standing on a train platform. Two lightning bolts strike, one at each end of the platform, at exactly the same time. You're standing in the middle. The light from both strikes reaches you at the same moment. And since you know you're equidistant from both ends, you conclude that the strikes happened simultaneously. Now imagine someone is sitting on a train that's moving past the platform at very high speed. From their perspective on the moving train, the light from the front strike reaches them before the light from the rear strike. Not because light travels at different speeds in different directions. It doesn't. Light always travels at the same speed in all directions for all observers. But because the train is moving toward the light coming from the front strike and away from the light coming from the rear strike. Since the speed of light is constant for all observers, this is the absolute bedrock of special relativity, and the moving passenger received the front strike's light first. The moving passenger concludes that the front strike happened before the rear strike. They weren't simultaneous at all. Two observers watching the exact same pair of events arrive at different conclusions about whether those events happened at the same time. And here's the crucial thing. Neither observer is wrong. There's no preferred frame of reference in special relativity. No observer's perspective is more valid than any other's. The platform observer's conclusion that the strikes were simultaneous is exactly as valid as the train passenger's conclusion that they weren't. Both are correct within their own reference frames. In special relativity, there's simply no absolute answer to the question of whether two spatially separated events are simultaneous. The answer depends entirely on who's asking, on their state of motion relative to the events. For events connected by ordinary cause and effect, by signals traveling at or below the speed of light, this ambiguity in simultaneity doesn't create any problems at all. If I throw a ball and it breaks a window, every observer in the universe, regardless of how they're moving, regardless of their velocity or direction, will agree that I threw the ball before the window broke. The cause always precedes the effect. Always. Without exception. Special relativity guarantees this for any pair of events connected by signals that travel at or below the speed of light. The Lorentz transformations, the mathematical equations that translate between different observers' measurements of space and time, are structured in such a way that causal order is always preserved for subluminal connections. This is not an accident or a coincidence. This preservation of causal order is the foundation on which all of physics rests. Every physical law, every prediction, every experiment depends on the idea that causes come before their effects. Without this ordering, you can't predict anything. You can't explain anything. Science itself becomes incoherent because the very act of doing science, observing the present state of a system, using physical laws to predict its future state, and then checking whether your prediction is correct, is itself a causal chain. If effects can precede their causes, this chain becomes a loop, and the entire structure of scientific reasoning collapses into contradiction. But here's where tachyons enter the picture, and here's where everything begins to unravel. The preservation of causal order only holds for events connected by signals traveling at or below the speed of light. This is a mathematical fact, not an assumption or an approximation. It falls directly and unavoidably out of the structure of the Lorentz transformations. These equations contain a sharp boundary. If a signal connecting two events travels at or below light speed, then all observers in all inertial reference frames agree on the temporal order of those events. The cause comes first. The effect comes second. Always, no exceptions. But if a signal connecting two events travels faster than light, this guarantee vanishes completely. The Lorentz transformations no longer enforce a consistent ordering. Different observers, moving at different velocities, can see those same events in different temporal orders. One observer might see event A happen before event B. Another observer, equally valid, equally real, moving at a different velocity relative to the first, would see event B happen before event A. The temporal order of the events depends entirely on who's watching, and since no observer's frame is privileged, since special relativity treats all inertial frames as equally valid, both orderings are equally real. Neither is the correct one. Both are. This isn't a hypothetical edge case. It isn't something that only happens under extreme or unlikely conditions. It's a direct, unavoidable, mathematically rigorous consequence of combining faster than light signaling with the basic principles of special relativity. If tachyons exist and can carry any form of information, then the temporal order of cause and effect becomes observer-dependent for events connected by those tachyons. What one person sees as a cause, another person sees as an effect. What one person sees as the message being sent, another person sees as the message arriving. The very concept of before and after, the ordering that makes the universe intelligible, loses its universal meaning when tachyons are involved. And this is just the beginning. Because when you follow this logic to its full conclusion, when you carefully work through what happens when two observers each have access to tachyon communication, you don't just get confusion about which event came first. You get paradoxes, genuine, formal, inescapable logical contradictions where events cause themselves not to happen, where messages arrive before they're sent, where decisions made in the future reach back and reshape the past. The mathematics is clear, rigorous, and devastating in its implications. The speed of light isn't just a speed limit imposed by nature for arbitrary reasons. It's the speed that holds cause and effect together. It's the scaffolding that keeps the universe logically self-consistent. It's the reason that what happened yesterday can't be rewritten by what happens tomorrow. And a tachyon, by moving faster than this speed, wouldn't just be a fast particle. It would be a fracture in the logical architecture of reality itself. To understand why a faster than light particle would shatter causality, we need to look more closely at how special relativity actually describes the relationship between space and time. Not as separate things, not as independent dimensions that happen to coexist, but as a single interwoven fabric that Einstein called space-time. This concept, space-time, is one of the most important ideas in all of physics, and it's the key to understanding exactly how tachyons create paradoxes that aren't just strange or counterintuitive, but logically impossible. Before Einstein, people thought of space and time as completely separate things. Space was the stage on which events happened. Time was the clock that ticked while they happened. Space had 3 dimensions: up and down, left and right, forward and backward. Time had 1 dimension, from past to future. They were independent, separate, unrelated. You could change your position in space without affecting your position in time. You could move through time without moving through space. They were like 2 different books sitting on the same shelf, related only by proximity, not by any deeper connection. Einstein showed this was wrong. Space and time aren't separate. They're woven together into a single 4-dimensional structure. When you move through space, you also affect how you move through time. When you change your velocity, you don't just change how fast you're covering distance, you change the rate at which time passes for you. You change what you consider to be simultaneous events. You change, in a very real and measurable sense, the shape of your experience of reality. This isn't philosophy, it's physics, measured, confirmed, and used every day in technologies that depend on precise timekeeping. The mathematician Hermann Minkowski, who had actually been one of Einstein's professors, formalized this idea in 1908. He showed that the correct way to think about events in the universe is not as points in 3-dimensional space that exist at moments in 1-dimensional time, but as points in 4-dimensional space-time. An event is something that happens at a specific place and a specific time. A firecracker is going off, a clock ticking, a photon is being emitted. Each event is a single point in space-time, defined by 4 numbers, 3 for its spatial location and 1 for its time. Minkowski introduced a mathematical tool for measuring the separation between events in space-time. In ordinary space, you measure distances using the Pythagorean theorem. The distance between 2 points is the square root of the sum of the squares of the differences in their coordinates. It's straightforward. But in space-time, the formula is different, crucially different. Instead of adding the squares of the space differences and the square of the time difference, you subtract. The space-time interval between 2 events involves the time separation squared minus the space separation squared, with appropriate factors of the speed of light to make the units work. This subtraction sign changes everything. It's the mathematical heart of special relativity, and it's what makes faster than light travel so problematic. This subtraction creates 3 fundamentally different types of separations between events. 3 categories that determine the causal relationship between any 2 events in the universe. The first type is called a time-like interval. This is what you get when the time separation between 2 events is larger than their space separation divided by the speed of light. In plain language, this means that a signal traveling at the speed of light or slower could connect the 2 events. There's enough time between them for light to travel from one to the other. Events, separated by a time-like interval, can be causally connected. One can cause the other. You can throw a ball from one event and have it arrive at the other event. You can send a flash of light, a radio signal, or a message. There's a physical pathway connecting them. For events separated by a time-like interval, all observers in all reference frames agree on which event happened first. This is the mathematical guarantee I mentioned earlier. It doesn't matter how fast you're moving, what direction you're traveling, or where you are in the universe. If two events are separated by a time-like interval, every observer will say the earlier one happened before the later one. The causal order is absolute, universal, and unambiguous. This is why causality works in our everyday world. Every cause and effect pair you've ever experienced, every ball thrown and caught, every word spoken and heard, every button pressed and light turned on, involved events separated by time-like intervals. The cause could send a signal to the effect, because there was enough time for that signal to travel the distance. And because the interval was time-like, everyone agreed on which event was the cause and which was the effect. The second type is called a light-like interval, or a null interval. This is the boundary case. The time separation exactly equals the space separation divided by the speed of light. Only light itself, traveling at exactly the speed of light, could connect these two events. Photons live on light-like intervals. Their entire existence traces a path through space-time along these intervals. For events separated by light-like intervals, the causal ordering is still preserved. All observers agree on the order. The third type is where things get dangerous. It's called a spacelike interval. This is what you get when the space separation between two events is larger than their time separation multiplied by the speed of light. In plain language, there's too much space between them and not enough time for even light to travel from one to the other. No signal traveling at the speed of light or slower can connect these two events. They're too far apart and too close together in time. There's simply no way for one event to influence the other if the fastest possible signal travels at the speed of light. Events separated by a space-like interval are, in the framework of standard physics, causally disconnected. Neither one can affect the other. They might as well be in separate universes as far as cause and effect are concerned. And here's the critical property of space-like intervals. For events separated by a space-like interval, different observers can disagree about the order in which they happened. Not just about whether they were simultaneous, about the actual order. Observer A might say event 1 happened before event 2. Observer B, moving at a different velocity, might say event 2 happened before event 1. And observer C, moving at yet another velocity, might say they happened at exactly the same time. All three observers are correct. None of them is wrong. The temporal ordering of space-like separated events is not a property of the events themselves. It's a property of the observer. It depends on your frame of reference. It depends on how you're moving. Now, in ordinary physics, this ambiguity in the ordering of space-like separated events doesn't cause any problems, because space-like separated events can't influence each other. No signal can travel between them. If I can't send a message from event 1 to event 2, because they're too far apart in space and too close together in time, then it doesn't matter whether you think event 1 happened first or event 2 happened first. The ordering is ambiguous, but the ambiguity is harmless because the events are causally independent. They have no effect on each other. Who cares which one happened first if neither one caused the other? But a tachyon would change everything. A tachyon, by definition, moves faster than light. This means a tachyon can travel between events that are separated by space-like intervals. It can cross distances that light cannot cross in the time available. It can connect events that, in ordinary physics, are supposed to be causally disconnected. And this is where the nightmare begins. Because those space-like separated events the ones whose temporal ordering depends on the observer, are exactly the events that a tachyon would connect. A tachyon doesn't just travel faster than light. It specifically travels through the region of space-time where temporal ordering breaks down. It specifically connects events whose before and after are observer dependent. Let me make this concrete with a thought experiment. Imagine two space stations floating in deep space. Let's call them Station Alpha and Station Beta. They're separated by a distance of 10 light minutes. That means light takes 10 minutes to travel from one to the other. Both stations have clocks that are synchronized. They agreed on a time system beforehand. Now, Station Alpha has a tachyon transmitter, a hypothetical device that can send a tachyon signal at, say, 5 times the speed of light. At exactly 12 noon, according to Alpha's clock, an operator at Alpha sends a tachyon message to Beta. The message says simply, "Hello." The tachyon travels at 5 times the speed of light, so it covers the 10 light-minute distance in 2 minutes. The message arrives at Station Beta at 12:02, according to Alpha's frame of reference. So far, this seems straightforward. A message was sent at noon. It arrived at 2 minutes past noon. Cause before effect. Sending before receiving. Nothing unusual. Everything seems fine from this perspective. But now let's look at this same pair of events from a different frame of reference. Let's say there's an observer on a spacecraft moving at a significant fraction of the speed of light relative to the two stations. This observer is watching the same events, the sending of the tachyon at Alpha and the receiving of the tachyon at Beta. But because of the way the Lorentz transformations work, because of how space and time transform between moving reference frames, this observer doesn't see the same timing. The Lorentz transformations tell us exactly how to calculate what this moving observer sees, and the mathematics is unambiguous. For a signal traveling faster than light, there exist valid reference frames, frames occupied by observers moving at perfectly ordinary subluminal speeds, in which the tachyon signal arrives at Beta before it was sent from Alpha. Let me say that again because it's important. The moving observer, a person traveling at an ordinary, everyday speed, well below the speed of light, using perfectly standard clocks and rulers, following all the laws of physics, would calculate and measure that Station Beta received the tachyon message before Station Alpha sent it. Not at the same time, before. The effect preceded the cause. The arrival happened before the departure. The answer came before the question. And this isn't because the moving observer's clocks are wrong or their measurements are flawed. Their clocks and measurements are just as valid as anyone else's. Special relativity is explicit about this. All inertial reference frames are equally valid. There is no preferred frame. There is no correct frame. The station frame, where the message was sent before it was received, is valid. The spacecraft frame, where the message was received before it was sent, is equally valid. Both descriptions are true. This result falls directly out of the Lorentz transformations. There's no way to avoid it, no way to modify the mathematics to prevent it, no clever workaround that preserves faster than light signaling while also preserving a universal causal order. The two are mathematically incompatible. You can have faster than light signaling or you can have a universal causal order, but you cannot have both. The mathematics doesn't allow it. Let me walk through the logic one more time to make sure the mechanism is absolutely clear. When two events are connected by a signal traveling slower than light, they're separated by a time-like interval. The mathematics of the Lorentz transformations guarantees that all observers will agree on which event happened first. The The time order is locked in. It's invariant. It's the same for everyone. No matter how fast you're moving, no matter in what direction, the sending always happens before the receiving. But when two events are connected by a tachyon, a signal traveling faster than light, those events are separated by a spacelike interval. And for spacelike intervals, the Lorentz transformations do not lock in the time order. The order can flip depending on the observer's velocity. Some observers will see the sending first, others will see the receiving first. The time order is not invariant. It's frame dependent. It changes depending on who's watching. To understand viscerally why this happens, you have to understand what the Lorentz transformations actually do to time. When you switch from one reference frame to another, you're not just adjusting for the difference in position or the difference in clock synchronization. You're mixing space and time together. In the Lorentz transformations, what one observer calls pure time, another observer calls a mixture of time and space, and what one observer calls pure space, another observer calls a mixture of space and time. Space and time rotate into each other when you change reference frames, similar to how the x and y axes of a coordinate system rotate into each other when you turn the coordinate system. For events that are close together in space and far apart in time, this mixing is small. The time component dominates, and even after the transformation, the events are still in the same time order. But for events that are far apart in space and close, together in time, which is exactly the situation when a tachyon connects them, the mixing can be large enough to flip the sign of the time difference. What was positive becomes negative. What was before becomes after. The cause becomes the effect. This isn't a paradox yet. Having different observers disagree about the order of two events is strange, but by itself, it's not a logical contradiction. It becomes a contradiction only when you can close the loop, when the reversal of cause and effect can be used to create a situation that's logically impossible. And that's exactly what happens when you combine tachyons with the principle of relativity. But before we get to that, let me make the physics of the event order reversal even more concrete. Consider a specific numerical example. Station alpha and station beta are 10 light minutes apart. Alpha sends a tachyon signal at 5 times the speed of light. The signal leaves alpha at time 0 and arrives at beta at time plus 2 minutes, as measured in the station's rest frame. Now, consider an observer moving at 60% of the speed of light relative to the stations, in the direction from alpha toward beta. Using the Lorentz transformation equations, we can calculate exactly what this observer measures. The time of the sending event at alpha transforms straightforwardly, but the time of the receiving event at beta, which involves both a time component and a significant spatial component due to the distance between the stations, transforms differently. When you plug in the numbers, the receiving event at beta, as measured by the moving observer, occurs at a negative time relative to the sending event. The tachyon arrives before it was sent. Not by some exotic or barely measurable amount, by a substantial, clearly measurable margin. The faster the tachyon travels, the more pronounced this reversal becomes. A tachyon traveling at 10 times the speed of light would show an even larger reversal. A tachyon traveling at 100 times the speed of light, larger still. And a tachyon with 0 energy, traveling at infinite speed, would show the maximum possible reversal. In that case, every observer who is moving relative to the stations would see the arrival before the departure. The effect would precede the cause for essentially everyone except those at rest relative to the stations. Now, you might think there's an easy solution here. You might think we could just pick one reference frame and declare it the real one. We could say that the station's rest frame is the correct frame, and the moving observer's frame is somehow wrong or less valid. If we could do that, we could say the message really was sent before it was received, and the moving observer is just seeing things differently because of their motion. Problem solved. But this solution is exactly what special relativity forbids. The entire foundation of relativity rests on the principle that all inertial reference frames are equally valid. There is no preferred frame. There is no absolute rest. There is no way to say that one observer's measurements are more real than another's. This principle isn't optional. It isn't a philosophical preference that you can discard when it becomes inconvenient. It's built into the structure of the theory. Every experimental test of special relativity confirms it. Every prediction that depends on it, from the behavior of particles in accelerators to the precision of GPS satellites, has been verified. If you abandon the principle of relativity, you don't just fix the tachyon problem. You destroy all of special relativity, which means you destroy general relativity too, which means you lose our understanding of gravity, of black holes, of the expansion of the universe, of GPS, of particle physics, and of nuclear energy. You lose all of modern physics, essentially. That's not a trade anyone is willing to make. So we're stuck. If tachyons exist, different observers will see cause and effect, in different orders, and all of those observers are equally correct. There is no fact of the matter about which event happened first when a tachyon connects them. To visualize all of this, physicists use something called a light cone diagram. Imagine a point in space-time, a specific event. From that event, draw all the paths that light could follow, moving outward in all directions. Since light travels at a fixed speed, these paths form a cone shape when you plot them on a diagram, with time going upward and space going sideways. The upward opening cone above the event is called the future light cone. It contains all the events that the original event could potentially cause. All the events that a light signal or a slower signal could reach. If you send a flash of light from the original event, it will eventually reach any event inside the future light cone. The downward opening cone below the event is called the past light cone. It contains all the events that could have caused the original event. All the events from which a signal could have arrived at the original event. Everything inside the past light cone could, in principle, have influenced the original event. Inside the light cones is the time-like region. Events here are causally connected to the original event. Their ordering relative to the original event is absolute. Everyone agrees on whether they happened before or after. Outside the light cones is the spacelike region. Events here cannot be reached by light or anything slower. They're causally disconnected from the original event in standard physics. And critically, their temporal ordering relative to the original event is observer dependent. Some observers will say they happened before the original event. Others will say they happened after. Others will say they happened at the same time. A tachyon, because it moves faster than light, travels outside the light cone. Its path on a space-time diagram extends into the spacelike region. It connects events that lie outside each other's light cones. And because those events are in the spacelike region, their temporal ordering is not fixed. The tachyon specifically travels through the part of space-time where cause and effect lose their universal meaning. This is why the speed of light is so important. It's not just a speed. It's the boundary of the light cone. It's the edge of the causal structure of space-time. Everything inside the light cone follows causal rules that everyone agrees on. Everything outside the light cone does not. The speed of light is the speed of causality itself. Anything that moves within this boundary preserves the logical structure of the universe. Anything that crosses it threatens to destroy that structure. There's something deeply important buried in all of this that's worth stating explicitly. The problem with tachyons is not that we don't have the technology to detect them. It's not that our experiments aren't sensitive enough. It's not that they're hiding somewhere beyond our current reach. The problem is structural, it's mathematical, it's logical. The Lorentz transformations, the equations that form the backbone of special relativity, make a very specific mathematical statement. They say that any signal connecting two space-like separated events will have an observer-dependent temporal ordering. This is not a bug in the equations. It's a feature. It's how space-time works. It's the mathematical expression of the fact that causality has a speed limit, and that speed limit is the speed of light. When you ask what would happen if a tachyon existed, you're asking the Lorentz transformations to do something they explicitly forbid. You're asking them to maintain a consistent causal ordering for a signal that travels through the space-like region of space-time. And the answer is, they can't. They refuse. The mathematics will not cooperate. No matter how you set up the problem, no matter what assumptions you make, no matter how cleverly you try to arrange things, the Lorentz transformations will always produce reference frames in which the tachyon arrives before it departs. This is why physicists take the tachyon problem so seriously. It's not a matter of engineering or technology, it's a matter of logic. The existence of a detectable, information-carrying tachyon would create a logical contradiction within the framework of special relativity. And special relativity is not optional. It's confirmed by over a century of precision experiments. It's built into the standard model of particle physics. It's the foundation of quantum field theory. It underlies every successful prediction in modern physics. You can't modify it or discard it without losing everything we know about how the universe works at a fundamental level. Now, you might wonder whether this is really as bad as I'm making it sound. After all, having different observers disagree about the order of events is strange, but is it really a disaster? Maybe we could just live with the ambiguity. Maybe we could accept that some events don't have a well-defined order and move on. If the disagreement were confined to events that can't influence each other, that would be fine. And in standard physics, that's exactly what happens. Different observers can disagree about the ordering of space-like separated events, but since those events can't influence each other anyway, the disagreement is harmless. It's a curiosity, not a crisis. But the tachyon changes this completely. The tachyon creates a physical connection between space-like separated events. It carries energy, momentum, and potentially information across the space-like gap. And once you have a physical connection between events whose ordering is ambiguous, the ambiguity is no longer harmless. It becomes catastrophic. Because now you're not just disagreeing about the ordering of disconnected events. You're disagreeing about which end of a physical interaction is the cause, and which is the effect. You're disagreeing about whether a signal was sent or received. You're disagreeing about the direction of information flow. And when different observers disagree about the direction of information flow, you can set up situations where information flows in a circle, creating causal loops and logical paradoxes that have no resolution. think about what it would mean for a message to arrive before it's sent. Not in some abstract philosophical sense, but in a concrete physical sense. The receiver reads the message. They act on it. They make decisions based on its content. They change their behavior. All of this happens before the sender has decided to send it, before the sender has composed it, before the sender even knows they're going to send it. The effect of the message exists before its cause. The response exists before the stimulus. The answer exists before the question. This isn't time dilation, where time simply runs at different rates for different observers, but everyone still agrees on the order of causally connected events. This isn't the relativity of simultaneity for causally disconnected events, which is strange but harmless. This is something far more radical. This is the reversal of the causal arrow for events that are physically connected by the tachyon signal, and it doesn't require any exotic technology to observe. It doesn't require the observer to be moving at the speed of light or anything close to it. An observer moving at a modest fraction of the speed of light, a perfectly ordinary speed by astrophysical standards, would see the event order reversal for a tachyon traveling at just a few times the speed of light. The faster the tachyon, the slower the observer needs to be moving to see the reversal. For a sufficiently fast tachyon, almost any moving observer would see the effect before the cause. The universe, as described by special relativity, has a very specific architecture. Events are organized into a causal structure defined by light cones. Inside the light cones, causality is absolute. Outside the light cones, temporal ordering is relative. This architecture is elegant, consistent, and incredibly well tested. Every experiment we've ever performed is consistent with it. Every prediction it makes has been confirmed. It works. And a tachyon would violate this architecture in the most fundamental way possible. It would connect the region where causality is absolute to the region where temporal ordering is relative. It would bridge the gap between the inside and the outside of the light cone. It would link cause and effect across the spacelike frontier where the very concept of before and after has no fixed meaning. The implications of this extend far beyond just one particle or one signal. If tachyons existed, the entire causal structure of space-time would be compromised. Every event in the universe would potentially be connected to events outside its light cone, events whose temporal ordering is ambiguous. The neat division between what can cause what and what can't would dissolve. The past would no longer be sealed off from the future. And this isn't just an abstract philosophical worry. When you work through the specific scenarios, when you set up concrete situations involving two observers, both capable of sending and receiving tachyon signals, you don't just get confusion or ambiguity. You get machines that receive their own messages before sending them. You get closed loops where information circulates endlessly with no origin. You get paradoxes where the very act of receiving a message prevents the message from ever being sent. The mathematics leads inexorably to logical contradictions that have no resolution. And those contradictions are the strongest evidence we have that tachyons, despite being allowed by the mathematics of special relativity in isolation, cannot exist in a universe that also obeys the principle of relativity and maintains a coherent causal structure. The equations allow tachyonic solutions in isolation, but the causal architecture of space-time will not accommodate them. The result is not mere ambiguity. It is an outright contradiction, and contradiction is where physics draws its hardest line. So far, We've established that a tachyon travelling between 2 points would have its temporal ordering reversed in certain reference frames. Some observers would see the signal arrive before it was sent. That alone is deeply strange, but it's not yet a logical contradiction. It's weird. It's unsettling. It violates our intuition about how time works. But a single tachyon signal travelling from one point to another, even if some observers see it arrive before it departs, doesn't by itself create an impossible situation. The sender sends, the receiver receives. Different observers disagree about the order, but nothing logically impossible has happened. The paradox, the real paradox, the one that makes physicists genuinely conclude that information carrying tachyons cannot exist, requires something more. It requires 2 tachyon signals, 2 observers, and a return message. This is the tachyonic antitelephone, and it is one of the most devastating thought experiments in all of physics. More devastating in some ways than any experiment that could be performed in a laboratory, because it shows not merely that something is unlikely or unobserved, but that something is logically forbidden. The tachyonic antitelephone was first described in detail by Gregory Benford, David Book, and William Newcomb in 1970. The name is deliberate. A telephone sends messages forward in time. An antitelephone sends messages backward in time. Not metaphorically, not as a figure of speech, literally. The tachyonic antitelephone is a device that, using nothing more than the established physics of special relativity combined with faster-than-light signaling, can send information into its own past. And this isn't a flaw in the argument. It isn't a mistake in the mathematics. It's the inevitable, inescapable conclusion of combining 2 things that each seem perfectly reasonable on their own. Faster-than-light particles and the principle of relativity. Put them together and you get a time machine. Not the kind from science fiction with spinning wheels and flashing lights. Something far worse. A logical impossibility. Let me walk you through exactly how this works, step by step. No tricks, no hidden assumptions, just the Lorentz transformations applied to 2 tachyon signals. We need 2 observers. Let's call them Alice and Bob. Alice is sitting in a laboratory on Earth. Bob is on a spacecraft moving at a significant fraction of the speed of light relative to Alice. Let's say Bob is moving at 60% of the speed of light. This is a fast speed by everyday standards, but it's well below the speed of light. Bob is a perfectly ordinary observer in a perfectly valid inertial reference frame. Nothing exotic about his situation at all. Both Alice and Bob have tachyon transmitters and receivers. These are hypothetical devices, of course. No such technology exists. But we're exploring what would happen if it did. Both devices can send and receive tachyon signals that travel at, say, 3 times the speed of light, as measured in the sender's own reference frame. This is an important detail. The tachyon travels at 3 times the speed of light relative to the person sending it, as measured in their rest frame. Here's the sequence of events. At a time, both Alice and Bob agree to call time 0. Alice sends a tachyon message to Bob. The message is simple. It says, "Hello, Bob." In Alice's reference frame, this tachyon travels at 3 times the speed of light. It covers the distance to Bob and arrives at Bob's location. Alice measures this and sees the signal arrive at Bob at some positive time after she sent it. From Alice's perspective, everything looks normal. She sent a message and it arrived later, 'cause before effect. No problem. But now we need to figure out what Bob sees. And this is where the Lorentz transformations come in. Bob is moving at 60% of the speed of light relative to Alice. Because of the way special relativity works, Bob's measurements of space and time are different from Alice's. They have to be. The Lorentz transformations tell us exactly how to convert between their measurements. And when we apply those transformations to a signal traveling at 5 times the speed of light in Alice's frame, something remarkable happens. In Bob's reference frame, the tachyon from Alice doesn't arrive at a later time. It arrives at an earlier time. According to Bob's perfectly valid clocks and rulers, Alice's message reaches him before she sent it. This is exactly what the Lorentz transformations predict. A tachyon signal can have its temporal ordering reversed in a moving frame. Bob sees the reception happen before the transmission. Now, here's the critical next step. This is where the antitelephone is actually constructed. Bob receives Alice's message. He reads it. He understands it. And then Bob decides to send a reply. He uses his own tachyon transmitter to send a message back to Alice. His message says, "Hello, Alice. I got your message." Bob sends this reply using a tachyon that travels at 3 times the speed of light in his reference frame. Not Alice's frame, Bob's frame. This is crucial. The tachyon Bob sends travels at 5 times the speed of light as measured by Bob, using Bob's clocks and rulers. Now we need to figure out when Alice receives Bob's reply. And this is where the mathematics becomes devastating. Bob is moving at 60% of the speed of light relative to Alice. The tachyon Bob sends is traveling at 5 times the speed of light in Bob's frame. When we use the Lorentz transformations to figure out what this looks like in Alice's frame, we find that Bob's reply signal arrives at Alice at a time that is before the time Alice sent her original message, not before Bob sent his reply. Before Alice sent the original message that started the whole exchange. Alice received Bob's response before she ever decided to contact Bob. Before she ever picked up the transmitter. Before she ever composed the word, "hello." The reply to her message arrives in her past. Let me say that once more because it's the heart of the entire argument. Alice sends a message to Bob at time 0. Because of the Lorentz transformations and the way tachyon signals behave in different reference frames, the entire exchange, Alice's message to Bob and Bob's reply back to Alice, completes in such a way that Alice receives the reply before she sent the original message. A round-trip message has been sent into the past. Information has traveled backward in time, not in some observer-dependent, ambiguous way. In Alice's own frame, by her own clocks, in her own experience. She receives a reply to something she hasn't done yet. And no exotic physics was used. No wormholes, no warped space-time, no fictional technology beyond the tachyon transmitters themselves. The only ingredients were the Lorentz transformations, which are confirmed physics, and tachyon signals, which are the hypothetical elements. The backward time travel didn't require any special trick. It emerged automatically from the standard physics of reference frame transformations. 2 perfectly valid observers, 2 perfectly valid tachyon signals. Each signal travels faster than light in its sender's frame, and the result is a message from the future arriving in the past. This is the tachyonic antitelephone. And notice what's happened. We haven't violated any individual step. Each step is perfectly logical on its own. Alice sends a tachyon. Fine. The tachyon's temporal ordering is reversed in Bob's frame. We've already shown why this happens. It's a consequence of the Lorentz transformations for spacelike intervals. Bob receives the message and sends a reply. Fine. Bob's reply tachyon has its temporal ordering reversed in Alice's frame for exactly the same mathematical reason. Each individual piece is consistent with the physics of special relativity, but when you put them all together, the result is a closed loop, where a message arrives before it was sent. The antitelephone doesn't require anything beyond what the Lorentz transformations already tell us. It's not an edge case or a peculiar arrangement. Any two observers moving relative to each other who can both send and receive tachyon signals can construct an antitelephone. The mathematics guarantees it. You cannot avoid it as long as faster than light signaling exists and the principle of relativity holds. Now, let's think about what this actually means. Because a message from the future arriving in the past isn't just strange, it's the doorway to logical contradictions that have no resolution. Imagine Alice decides to use the antitelephone in a specific way. She programs her equipment with a simple rule. If she receives a message from Bob saying, "Hello Alice, I got your message," then she will not send the original message. She will deliberately refrain from sending anything. She will put down the transmitter, walk away, and do nothing. Think about what happens. Follow the chain carefully. If Alice doesn't send the original message, then Bob never receives it. If Bob never receives it, he has nothing to reply to. He never sends a reply. If he never sends a reply, Alice never receives the reply. If Alice never receives the reply, she has no reason not to send the original message. There's no warning, no signal from the future telling her to refrain. So she sends it. But if she sends it, Bob receives it. Bob composes his reply. Bob sends his reply. Alice receives that reply in her past. And her programmed rule kicks in. And she doesn't send the message. We're going in circles. The chain of logic chases its own tail endlessly. The event causes itself not to happen. And not happening causes it to happen. There is no consistent solution. No matter what Alice does, she is contradicted by the consequences of her own actions. If she sends the message, the chain of events ensures she doesn't send it. If she doesn't send it, the chain of events ensures she does. This is a genuine logical paradox, not a puzzle with a clever solution, not a riddle that resolves when you think about it carefully enough. A true contradiction. A situation where the universe would need to be in two mutually exclusive states simultaneously. The message was both sent and not sent. The reply both exists and doesn't exist. There is no self-consistent history. No set of events can occur without contradicting itself. The universe, as described by physical laws, must have consistent histories. Events must be able to happen in a way that doesn't produce logical contradictions. This is not a law we imposed on the universe from outside. It's a requirement of logic itself. A universe that contains contradictions is a universe where anything is true and nothing is false, where predictions are meaningless, where science is impossible. A universe that allows the tachyonic antitelephone is a universe that allows this kind of contradiction. And a universe that allows this kind of contradiction is not a universe at all. It's gibberish. This is often compared to the grandfather paradox from science fiction. You travel back in time and prevent your own grandfather from meeting your grandmother. If they never meet, your parent is never born. If your parents were never born, you're never born. If you're never born, you never travel back in time. If you never travel back in time, your grandparents meet normally. Your parent is born, you're born. You travel back in time, and you prevent them from meeting again. Round and round forever. No consistent resolution. No stable state of affairs. Every possibility undermines itself. The tachyonic antitelephone produces exactly this kind of paradox, but it doesn't require a time machine in the science fiction sense. It doesn't require anyone to physically climb into a device and travel backward through the years. It doesn't require wormholes or warp drives or any technology beyond our current understanding of physics, except for the tachyons themselves. It only requires two observers who can send faster than light signals. That's it. Two people, two transmitters, two receivers. The backward time travel emerges from physics, automatically and unavoidably. The Lorentz transformations do all the work. The paradox builds itself, and the paradox isn't limited to the specific scenario I described. Any use of a tachyonic antitelephone that creates a causal loop, where information from the future influences events in the past, has the potential to create contradictions. Alice could use the antitelephone to warn herself about a stock market crash. She could warn herself about an accident. She could send any information at all to her own past. And in every case, the question arises, what if she uses that information to change the events that led to the information being sent? What if the warning prevents the crash? Then there's nothing to warn about. So no warning is sent. So the crash happens. So the warning is sent. Around and around. Some people try to resolve this by suggesting that maybe the universe would prevent the paradox somehow. Maybe there's a cosmic censorship principle that stops paradoxical loops from forming. Maybe Alice's transmitter would malfunction at just the right moment. Maybe she'd trip on the way to the transmitter. Maybe she'd have a sudden change of heart. Maybe the tachyon signal would be absorbed by interstellar gas or scattered by some random fluctuation before reaching Bob. These ideas fall under what physicists call the Novikov self-consistency principle, named after Russian physicist Igor Novikov. The principle states that any events that would create a paradox simply cannot happen. The universe would conspire somehow through ordinary physical processes to prevent them from occurring. Only self-consistent loops are allowed. History must be coherent, and if maintaining coherence requires a remarkable series of coincidences, then those coincidences will happen. This sounds reasonable at first glance, but it creates its own problems. It means the universe must somehow know in advance what actions would lead to paradoxes and prevent those specific actions from occurring. It means free will, or at least free action, is constrained by events that haven't happened yet. Alice can't choose to send the message because the universe needs her to send it to maintain consistency. Her actions in the present are determined by events in the future. This isn't cause and effect. This is effect and cause. The future determines the past. The effect determines the cause. And while this avoids logical contradictions in the strict sense, it introduces something almost equally disturbing. A universe where your actions are constrained not by the laws of physics operating forward in time, but by the requirement that the future be consistent with the past, which is itself determined by the future. It's circular. It's teleological. Physics doesn't work that way. Physical laws operate forward in time. The state of the universe at one moment determines the state at the next moment. The past causes the future. That's the direction of physical law. A universe with tachyonic antitelephones would require physical laws that operate in both directions simultaneously, with the future constraining the past just as the past constrains the future. This is so foreign to how physics works that it would essentially require a completely new framework for all of science. There's another attempted resolution that's worth addressing. Some people suggest that maybe tachyons exist, but can't carry information. If tachyons are real particles, but can't be controlled, can't be aimed, can't be modulated to encode messages, then maybe the antitelephone can't be built. If you can't send a deliberate signal using tachyons, then you can't create the causal loop, and the paradox doesn't arise. This is a more sophisticated objection, and it has some merit in certain theoretical contexts. There are models in quantum field theory where tachyonic excitations exist mathematically, but can't be used to transmit information faster than light. But the key point is this: if tachyons exist, but can't carry information, then they're not really the tachyons that people imagine when they hear the word. They're not particles you could detect with a tachyon receiver. They're not signals you could use for communication. They're mathematical features of a quantum field that have no direct physical observable corresponding to a faster-than-light particle. The tachyonic antitelephone argument specifically applies to tachyons that could, in principle, be detected and that carry some form of information or have some observable physical effect. If a tachyon interacts with matter in any detectable way, if it deposits energy, if it creates a signal, if it leaves any trace at all, then in principle, that interaction could be used to transmit information. And if information can be transmitted faster than light, the antitelephone can be built. Let me emphasize something easy to miss in all this discussion. The tachyonic antitelephone is not a practical engineering challenge. It's not something that would be difficult to build because of technological limitations. It's something that's impossible to build because the universe doesn't allow the particles that would make it work. The thought experiment exists to show why those particles can't exist. It's a proof by contradiction. You assume tachyons exist. You apply the known laws of physics. You derive a contradiction. Therefore, the assumption must be wrong. Tachyons, at least in the form of detectable faster-than-light particles that can carry information, cannot exist. This type of argument is common in physics. Physicists frequently use thought experiments to explore the consequences of hypothetical scenarios. Einstein himself was famous for them. His thought experiments about riding alongside a beam of light, about elevators in free fall, about trains and lightning strikes, all of these were tools for exploring the logical consequences of physical principles. The tachyonic antitelephone is in this tradition. It's a thought experiment that reveals a deep truth about the structure of space-time. What the tachyonic antitelephone reveals is that the speed of light does more than measure how fast photons travel. It draws the border between a universe that makes sense and one that doesn't. I want to distinguish this very clearly from other things that might sound similar, but are fundamentally different. There are several phenomena in physics that involve time behaving in unusual ways, and it's important not to confuse them with the tachyon problem. Time dilation is real and well established. When you move fast, time passes more slowly for you relative to stationary observers. This has been confirmed countless times. Astronauts on the International Space Station age very slightly less than people on the ground. Clocks on GPS satellites tick at measurably different rates than clocks on Earth's surface. But time dilation doesn't reverse causality. It doesn't make effects come before causes. It just changes the rate at which time passes. Everyone still agrees on the order of causally connected events. If Alice sends Bob a lightspeed message and Bob replies at light speed, all observers agree that Alice sent before Bob received, and Bob replied before Alice received the reply. The timing might be stretched or compressed by time dilation, but the order never flips. Looking into the past is something we do every night. When you look at the stars, you're seeing light that left those stars years or centuries ago. When you look at the Andromeda galaxy, you're seeing it as it was 2.5 million years ago. But you're not changing the past by looking at it. You're not influencing it. You're passively receiving information that travel to you at the speed of light. The events you're seeing are over, done, finished. The light is just arriving late because it had a long way to travel. This has nothing to do with tachyons or backward causation. Quantum entanglement is sometimes described as involving faster-than-light connections between particles. And it's true that entangled particles exhibit correlations that seem to require some kind of instantaneous connection. When you measure one entangled particle, the state of the other particle is instantaneously determined, no matter how far apart they are. But crucially, quantum entanglement cannot be used to send information faster than light. This has been proven rigorously. The correlations only become apparent when you compare the measurements afterward, which requires ordinary communication at light speed or slower. You can't use entanglement to build a telephone. You can't use it to send a message. And therefore, you can't use it to build an antitelephone. Entanglement is strange, but it respects the light speed limit for information transfer. It doesn't create causal paradoxes. The tachyon problem is different from all of these. It's not about seeing the past. It's not about time flowing at different rates. It's not about correlations that look like faster than light connections, but aren't really. It's about a particle that literally physically travels faster than light and carries information as it goes. A particle whose arrival at a destination precedes its departure from its origin in certain reference frames. A particle that, when combined with the principle of relativity, enables a device that can send messages into the past. Not metaphorical messages, real ones. With real content that can be read, understood, and acted upon before the sender decides to send them. This is retrocausation, genuine backward causation, the future influencing the past, not as a metaphor, not as a poetic description, as a literal physical process where events that have not yet occurred reach back and determine events that have already happened. And it's unique to the tachyon scenario because it's the only scenario in established physics where a physical entity could carry information across a spacelike interval, connecting events whose temporal ordering is observer-dependent. Every other strange time-related phenomenon in physics, dilation, looking at distant starlight, and entanglement keeps cause and effect safely intact. Only the tachyon threatens to reverse them. The depth of this problem cannot be overstated. It's not a quirk or an oddity or a fun puzzle for theoretical physicists to play with. It strikes at the foundations of everything we know about how the universe works. Causality. The principle that causes precede their effects isn't just a nice philosophical idea. It's embedded in the mathematical structure of every physical theory we have. Quantum mechanics, quantum field theory, general relativity, thermodynamics, and electromagnetism, all of them assume causality. All of them require that the present state of a system determines its future states, not the other way around. If you remove causality, if you allow the future to influence the past, then none of these theories work anymore. Their predictions become ambiguous or contradictory. The equations don't have unique solutions. The entire framework of physics collapses. This is why the tachyon is not just an interesting theoretical curiosity. It's a stress test for the logical structure of space-time. The tachyonic antitelephone demonstrates that if you take the equations of special relativity seriously, and everyone does because they've been confirmed by over a century of experiments, then faster than light. Information transfer is not merely difficult or impractical, it's logically forbidden. The universe cannot allow it without becoming self-contradictory. And a self-contradictory universe is not a universe that makes less sense. It's a universe that makes no sense at all. When physicists say tachyons can't exist, they often point to the lack of experimental evidence. And that's true. No tachyon has ever been detected. Every search has come up empty. But the argument from the tachyonic antitelephone is stronger than the argument from non-detection. Non-detection tells you that something probably doesn't exist. The antitelephone tells you that something can't exist, at least not as a detectable, information-carrying particle, without destroying the logical consistency of the universe. It is the difference between saying, "We haven't found any unicorns," and saying, "Unicorns are logically impossible." The first is an empirical statement. The second is a logical one. And logical impossibilities are much harder to overturn than empirical gaps. So where does this leave us? We started with a hypothetical particle that moves faster than light. We showed that the Lorentz transformations cause their temporal ordering to reverse in certain reference frames. We then showed that two observers exchanging tachyon signals can construct a device, that's the antitelephone, that sends information into the past. And we showed that this leads to logical paradoxes, grandfather-type contradictions that have no self-consistent resolution. The conclusion is stark and unavoidable. Either tachyons don't exist, or the principle of relativity is wrong, or causality doesn't work the way we think it does. These are the only three options. There is no fourth choice. Given that the principle of relativity is one of the most thoroughly tested principles in all of science, confirmed by every experiment that has ever been designed to test it, and that causality is the foundation of every physical theory we have, the most reasonable conclusion is that tachyons, in the sense of detectable faster-than-light particles that interact with ordinary matter, simply do not and cannot exist. The speed of light isn't just the fastest speed in the universe, it's the speed that keeps the universe from contradicting itself. It's the speed that keeps causation flowing in one direction, from earlier to later, never the reverse. It's the speed that makes cause and effect meaningful. It's the speed that makes physics possible. And any particle that violates this speed doesn't just break a rule, it breaks reality. So if tachyons are real, detectable, faster-than-light particles that would destroy causality, why do physicists still talk about them? Why does the word tachyon appear in serious physics papers, in textbooks, in discussions at conferences and universities around the world? The answer is surprising. The word tachyon in modern physics almost never refers to the kind of particle we've been discussing. It refers to something else entirely. Something mathematical. Something that lives in the equations of quantum field theory and string theory, but that doesn't correspond to a real particle zipping through space faster than light. Understanding this distinction is crucial because it's where most of the confusion about tachyons comes from. People hear physicists use the word tachyon and assume they're talking about faster than light particles. They're not. They're talking about a mathematical feature of certain theories, a feature that signals something important about those theories, but not the existence of superluminal particles. And the story of how the tachyon concept evolved from a hypothetical particle into a mathematical diagnostic tool is one of the more fascinating chapters in modern physics. In quantum field theory, particles aren't fundamental objects. Fields are. A particle is an excitation of a field, a ripple, a vibration. An electron is a ripple in the electron field. Photon is a ripple in the electromagnetic field. Every particle in the Standard Model is an excitation of some underlying quantum field that permeates all of space. The properties of these particles, their mass, their charge, and their spin, are determined by the properties of the fields they arise from. The mass of a particle in particular is related to a specific mathematical term in the field's equations. This term is called the mass squared parameter. For ordinary particles, this parameter is positive. A positive mass squared parameter means the field is stable. Its lowest energy state, its ground state, is a field value of 0 everywhere. Small disturbances in the field oscillate around this 0 value like a ball rolling back and forth at the bottom of a bowl. These oscillations are the particles. They propagate through space, interact with other fields, and behave the way particles should behave. Everything is well defined and sensible. But what happens when the mass squared parameter is negative? This is the situation that corresponds to a tachyonic field. And the answer is not that the field produces faster than light particles. The answer is far more interesting and far less exotic. The answer is that the field is unstable. A negative mass squared parameter means the field's energy is not at its minimum when the field value is 0. Instead, 0 is a maximum, a peak, a hilltop. The field is sitting at the top of a hill, not the bottom of a valley. And just like a ball balanced precisely on top of a hill will roll down at the slightest disturbance, the slightest breath of wind, the tiniest vibration, the field will rapidly shift away from 0 toward whatever value represents its true minimum energy state. This process is called tachyon condensation, and it's one of the most important concepts in modern theoretical physics. Even though its name is misleading. The tachyonic field doesn't produce faster than light particles that go zipping off through space, violating causality. It produces an instability that causes the field to change its value throughout all of space, rolling down from the unstable maximum to a stable minimum. The field evolves, settles, and finds its true ground state. Once the field reaches its new stable value, the instability disappears completely. The mass squared parameter at the new minimum is positive. The tachyonic behavior was never about real particles at all. It was about the field being in the wrong state, perched at an unstable maximum like water sitting above a drain, ready to flow downward at the first opportunity. The tachyonic mode is the mathematical alarm bell, the signal that says this configuration is unstable and the field needs to find its true ground state. And here is where it connects to one of the most important discoveries in modern physics. The Higgs mechanism, the process by which particles in the Standard Model acquire their mass, involves exactly this kind of tachyonic instability. The Higgs field has a potential energy function shaped like the bottom of a wine bottle. The center of the bottle, where the field value is 0, is a local maximum, not a minimum. If you tried to place the field at 0, it would be like balancing a ball at the very top of the bump in the center of the bottle's bottom. The field is unstable there. The mass squared parameter at that point is negative. The field is tachyonic, but the Higgs field doesn't stay at 0. It rolls down to the circular valley around the central bump. It settles at a non-zero value, a value we call the vacuum expectation value. This is the Higgs field's true ground state. At this new stable position, the mass squared parameter becomes positive. The instability is gone. The tachyonic mode has disappeared. And as a consequence of the field settling at this non-zero value, other particles that interact with the Higgs field acquire mass. The W and Z bosons, which carry the weak nuclear force, become massive. Quarks and leptons gain their masses. The entire mass structure of the Standard Model emerges from the Higgs field, finding its stable minimum after starting from a tachyonic, unstable configuration. So when particle physicists talk about the tachyonic nature of the Higgs field, they're not saying the Higgs boson travels faster than light. The Higgs boson is a perfectly ordinary particle that travels slower than light, with a mass of about 125 billion electron volts, confirmed by experiments at the Large Hadron Collider in 2012. What they're saying is that the mathematical structure of the Higgs field before it reaches its stable state has a negative mass squared parameter, the hallmark of a tachyonic instability. The tachyon here is a diagnostic, a warning light. It sees the field isn't in its lowest energy state yet. Once the field finds its minimum, the tachyon disappears, and normal physics resumes. This reinterpretation of the tachyon concept is one of the quiet triumphs of quantum field theory. The same mathematical structure that seemed to describe impossible, faster-than-light particles in classical special relativity turns out to describe something completely different in quantum field theory. It describes vacuum instability, the rolling of a field from a false vacuum to a true vacuum. A phase transition, similar in some ways to water freezing into ice or a magnet spontaneously aligning its domains. No faster-than-light particles are involved. No causality is violated. The mathematics is the same, the equations look identical, but the physical interpretation is entirely different. Tachyons also appear prominently in string theory, and there too they signal instability rather than faster-than-light travel. In the original formulation of bosonic string theory, one of the earliest versions of string theory that includes only bosons and no fermions, the lowest energy state of the string turns out to be tachyonic. It has a negative mass squared. When this was first discovered in the 1970s, it was considered a serious problem for the theory. It seemed to indicate that bosonic string theory was fundamentally flawed because it predicted the existence of a tachyon. Some physicists worry that this invalidated the entire string theory program before it had even properly begun. But over time, as the understanding of tachyonic instabilities in quantum field theory deepened, physicists came to understand that the tachyon in bosonic string theory means the same thing it means in field theory. It means the vacuum, the background state of the theory, is unstable. The theory is sitting at the top of a hill, not in a valley. It needs to roll down to its true minimum. The tachyon is the mathematical alarm bell announcing this instability, not a prediction of a real particle that violates causality. In later versions of string theory, specifically superstring theories that include both bosons and fermions and incorporate supersymmetry, the tachyon is absent. The theory is stable. The vacuum is a genuine minimum, not a maximum. This was considered a major achievement. Getting rid of the tachyon was a sign that the theory had found its proper ground state. The tachyon's absence meant the theory was well behaved. Its presence in the older version meant something was wrong, not that faster-than-light particles existed, but that the theory needed to be fixed or reinterpreted. In the late 1990s, physicist Ashoka Sen made a remarkable conjecture about the tachyon in bosonic string theory that transformed how physicists understood these mathematical objects. He proposed that the tachyon represents the instability of a particular type of object in string theory called a D-brane. D-branes are extended objects, surfaces, or membranes of various dimensions, on which the endpoints of open strings can attach. They are real dynamical objects in string theory, not just mathematical abstractions. They have energy, they have tension, and they can move through space. Sen argued that when a D-brane becomes unstable and begins to decay, when it dissolves and releases its energy, the tachyon in the string theory living on that brane is exactly the mathematical description of that decay process. The tachyon field rolls down from its unstable maximum. The brane dissolves into closed strings and radiation, and a new stable configuration is reached. This conjecture has been extensively tested and confirmed within the mathematical framework of string theory through increasingly sophisticated calculations. Once again, the tachyon turned out to describe not a faster-than-light particle, but a transition from an unstable state to a stable one. A phase transition, a rearrangement, not a violation of causality. Now let's turn to the experimental record, because regardless of what the mathematics says, physics is ultimately an experimental science. What have experiments actually found when looking for tachyons? The short answer is nothing. Absolutely nothing. No experiment has ever detected a tachyon. Not in particle accelerators at CERN or Fermilab or anywhere else. Not in cosmic ray observatories scanning the sky for high-energy particles from space. Not in astrophysical observations of distant galaxies, supernovae, or gamma-ray bursts. Not anywhere. Every dedicated search for faster-than-light particles has come up completely empty. And there have been searches. Physicists take seriously the possibility that their theories might be wrong, and they've looked for tachyons in several ways. One approach is to look for particles with imaginary mass. In practice, this means looking for particles whose energy-momentum relationship doesn't follow the normal pattern. For an ordinary particle, energy squared minus momentum squared times the speed of light squared equals mass squared times the speed of light to the fourth power. For a tachyon, this relationship would yield a negative value for mass squared. Experiments at particle accelerators have looked for this signature and found nothing. Every particle ever produced and detected follows the normal energy-momentum relationship with a positive or zero mass squared. Another approach is to look for Cherenkov radiation from tachyons. When an ordinary charged particle moves through a medium faster than the speed of light in that medium, not faster than light in vacuum, but faster than the reduced speed of light within that particular substance, it produces Cherenkov radiation, a cone of blue light, similar to a sonic boom, but with light instead of sound. This is the eerie blue glow you see in photographs of nuclear reactor pools. The particles in the reactor are moving through water faster than light travels through water, and the result is that distinctive blue luminescence. If tachyons existed and carried electric charge, they might produce a similar kind of radiation, even in a vacuum, since they'd be moving faster than the speed of light in a vacuum itself. This would be a distinctive and detectable signature. Searches for this kind of anomalous vacuum, Cherenkov radiation, have been conducted at multiple facilities over the years and have found nothing. No unexplained blue glow. No mysterious radiation with the telltale angular pattern of Cherenkov emission. Nothing at all. There have also been claims over the years of experimental evidence for faster-than-light phenomena, but none have withstood careful scrutiny. In 2011, the OPERA experiment at the Gran Sasso laboratory in Italy reported that neutrinos appeared to travel slightly faster than light over the 730-kilometer distance from CERN in Switzerland to Gran Sasso. The announcement sent shockwaves through the physics community and made headlines worldwide. Faster-than-light neutrinos would have been one of the most extraordinary discoveries in the history of science. It would have overturned over a century of established physics. Thousands of physicists around the world began analyzing the result, looking for errors, proposing alternative explanations, and designing independent experiments to check the measurement. After months of extensive investigation, the anomaly was traced to two mundane equipment problems. A faulty fiber optic cable connection was introducing a timing error, and a clock oscillator used for synchronization was slightly miscalibrated. When the equipment was repaired and the measurements were repeated, the neutrinos arrived exactly when they should have, traveling at the speed of light or very slightly below it, perfectly consistent with their tiny but non-zero mass. The episode was a valuable reminder that extraordinary claims require extraordinary evidence, and that subtle experimental errors are far more common than violations of fundamental physics. It also demonstrated the self-correcting nature of science. The error was found not by dismissing the result, but by taking it seriously enough to investigate it thoroughly. Other experiments have measured phenomena that superficially resemble faster-than-light propagation, but don't actually involve tachyons or information traveling faster than light. Quantum tunneling, for example, sometimes appears to allow particles to cross a barrier faster than light would take to cross the same distance. A particle hitting a barrier that it shouldn't be able to cross, according to classical physics, sometimes appears on the other side almost instantaneously. But careful analysis shows that no usable information is transmitted faster than light in these experiments. The apparent superluminal speed is a consequence of how the quantum wave function behaves during the tunneling process, not of any particle physically moving faster than light through space. The wave function doesn't represent a little ball flying through a wall at superluminal speed. It represents a probability distribution evolving in a way that creates the appearance of superluminal transit, without any actual information exceeding light speed. Similarly, the expansion of the universe can cause the distance between very distant galaxies to increase faster than the speed of light. But this is the expansion of space itself, the stretching of the fabric of space-time between objects, not the motion of objects through space. No information or energy is being transmitted faster than light in this process either. These are not tachyons by any definition. The experimental verdict is clear, consistent, and unambiguous. After decades of searching with increasingly sensitive instruments and increasingly powerful accelerators, after examining data from underground detectors and orbital observatories and every kind of experiment physicists could devise, no tachyon has been found. This absence of evidence doesn't prove tachyons don't exist. Strictly speaking, you can never prove a negative through experiment alone. Maybe tachyons interact so weakly with ordinary matter that our detectors can't register them. Maybe they exist in energy regimes we haven't explored yet. These possibilities can't be completely ruled out by experiment. But when you combine the experimental absence with the theoretical arguments we've discussed, the case against tachyons becomes overwhelming. The theoretical argument shows that information-carrying tachyons would create logical paradoxes. The experimental record shows no evidence that they exist. The quantum field theory interpretation shows that tachyonic mathematics describes vacuum instability, not faster-than-light particles. Every line of evidence points in the same direction. Tachyons, as real detectable faster-than-light particles, do not exist. I want to be precise about what we mean when we say tachyons can't exist, because the claim is more specific and more nuanced than it might sound at first. We're not saying the mathematics is wrong. The equations of special relativity genuinely do have solutions that describe faster-than-light motion. That's a mathematical fact. It's as solid as any other result in mathematics. And mathematical facts don't go away just because you don't like their implications. The solutions are there, sitting in the equations, perfectly well-defined and perfectly self-consistent at the level of the individual formulas. What we're saying is that these mathematical solutions don't correspond to anything in physical reality. The mathematics allows them, but the logical structure of the universe, the requirement that cause and effect be consistent and non-contradictory, forbids them from being realized as actual particles. This is an important distinction. Mathematics is a tool for describing reality, but not everything mathematics can describe actually exists. You can write equations for a sphere with a negative radius. The equations are valid, the mathematics works, but a sphere with a negative radius doesn't exist in physical space. Similarly, you can write equations for tachyons. The mathematics is self-consistent at the level of individual equations, but when you embed those equations in the full framework of special relativity, when you combine them with the principle of relativity and ask what happens when multiple observers interact using tachyon signals, you get contradictions. The equations work individually but fail collectively. The system is inconsistent even though the individual parts are not. This is actually a deep insight into the relationship between mathematics and physics. Physics doesn't just require that individual equations be self-consistent. It requires that the entire framework, all the equations working together, describing all possible observers and all possible interactions, be self-consistent. Tachyons pass the first test, but fail the second. They're mathematically valid in isolation, but physically impossible in combination with the rest of known physics. And this brings us to perhaps the deepest lesson of the tachyon story. Why does the speed of light play this special role? Why is it the boundary between causal and acausal? Why is it the speed at which the universe becomes logically consistent or falls apart? The answer is that the speed of light isn't really about light. Light happens to travel at this speed because light is massless, and massless particles must travel at this speed. But the speed itself is more fundamental than light. It's the speed of causality. It's the conversion factor between space and time. It's the constant that appears in the Lorentz transformations, in Einstein's field equations, and in the relationship between energy and mass. It would exist and have exactly the same value even if photons didn't exist, even if there were no such thing as light. The speed we call the speed of light is really the speed of space-time itself, the fundamental rate at which spatial distance converts to temporal duration. When Einstein wrote his 1905 paper on special relativity, he derived the theory from two postulates. First, the laws of physics are the same in all inertial reference frames. Second, the speed of light in a vacuum is the same for all observers. But the second postulate is actually more general than it sounds. It's not really about light specifically. It's about the existence of an invariant speed, a speed that's the same for everyone regardless of their motion. Einstein used light as his example because light was the most familiar thing that travelled at this speed. But the deep content of the postulate is that space-time has a geometry in which one particular speed is invariant, universal, the same in every reference frame. That speed turns out to be the maximum speed at which causal influence can propagate. It's the speed that separates the time-like region of space-time, where causal order is absolute, from the space-like region, where it's not. It's the speed that makes the Lorentz transformations preserve the ordering of cause and effect for any signal that doesn't exceed it. It's the structural constant of space-time geometry. This is why the speed of light feels like such a hard limit. It's not a speed limit in the way a highway speed limit is, something imposed from outside that could in principle be changed or violated. It's a structural feature of space-time itself. Asking why you can't go faster than light is a bit like asking why you can't go north of the North Pole. It's not that some force stops you, it's that the geometry of the space you're in doesn't allow it. The direction north ceases to exist at the North Pole. Similarly, faster than light speeds don't exist in the geometry of space-time as described by special relativity. Not because something prevents you from reaching them, but because the structure of space-time doesn't contain them as reachable states for massive objects. The Tachyon story teaches us something profound about the nature of physical law. Physical laws are not just descriptions of what happens. They're descriptions of what can happen and what cannot happen. And the boundary between the possible and the impossible isn't always set by practical considerations like available energy or existing technology. Sometimes it's set by logic. Sometimes the laws of physics rule things out, not because they'd require too much energy or too advanced a technology, but because they'd produce contradictions. The tachyon is ruled out by logic, not by engineering. No amount of technological progress will ever produce a detectable information-carrying tachyon, because the existence of such a particle is incompatible with the logical structure of space-time. This isn't a limitation we might overcome, it's a feature of reality we must accept. And there's something beautiful about this. The speed of light, this one particular speed, holds everything together. It connects space to time. It sets the boundary of causal influence. It ensures that the past stays in the past and the future stays in the future. It prevents paradoxes. It makes physics possible. Without this boundary, without this speed playing its structuring role, the universe would not be a place where events have definite causes and definite effects. It would not be a place where you could make predictions or test them. It would not be a place where science works. The speed of light is not a restriction. It's the architecture. We started this journey with a simple question. What would a tachyon really do? And the answer turned out to be far more devastating than just moving fast. A tachyon would unravel the causal structure of the universe. It would allow messages to be sent into the past. It would create logical paradoxes with no resolution. It would make the concept of cause and effect, the most fundamental organizing principle in all of science, meaningless. It would, in the most literal sense possible, break reality, not bend it, not stretch it, break it. And that's why it almost certainly cannot exist. Not because we haven't found one, not because our technology isn't good enough to detect one, not because our experiments aren't sensitive enough, or our accelerators aren't powerful enough, but because the logical architecture of space-time, the very structure that makes physics coherent and the universe intelligible, doesn't permit it. The equations of special relativity allow tachyonic solutions in isolation, but the full structure of space-time, with its light cones and its Lorentz invariance and its preservation of causal ordering, forbids them from manifesting as real, detectable particles. The mathematics permits it. The logic forbids it. And the universe, as far as every experiment and every observation has ever shown us, sides with the logic. The next time you see a beam of light, whether it's sunlight streaming through a window, a flashlight cutting through darkness, or the distant twinkle of a star, whose photons have traveled for years or centuries to reach your eyes, remember what that light represents. It's not just brightness. It's not just photons. It's the universe's speed limit, the maximum rate at which anything can influence anything else, the boundary between the knowable and the unknowable, between cause and effect, between what has happened and what hasn't happened yet. Every photon travels at exactly this speed, not faster, not slower, exactly. And that exactness, that precision, that absolute consistency is what keeps the universe coherent. It's what makes the past reliable and the future open. It's what allows events to have causes and predictions to have meaning. The speed of light is the heartbeat of space-time, steady, constant, and absolutely non-negotiable. And every hypothetical particle that would violate it, every tachyon that the mathematics can imagine but the universe refuses to produce, is a reminder that this speed is not arbitrary. It's essential. Without it, there is no before and after. Without it, there is no cause and effect. Without it, there is no story of the universe at all. Just a jumbled, contradictory mess of events with no order, no structure, and no meaning. The speed of light gives the universe its narrative. It gives time its direction. It gives reality its rules. And that, in the end, is why the tachyon remains forever on the other side of the boundary. Not because we can't reach it, but because reaching it would cost us everything that makes the universe a universe.